So, we're going to cover briefly some things that fall under the additional topics category. It equates to about 6 questions on the SAT, so it's not make or break. But some of these are actually pretty quick to do and not super complicated. There's a few tips and tricks, so any advantage you can get to get a few extra questions right is of benefit. Okay? First thing we're going to look at is some angle relationships, mostly being vertical angles. We have a figure drawn of 3 intersecting lines and some figures or some angles labeled. What's important to note is that on the front page of each section in math, man, you guys are like killing it today. Just way to be Johnny on the spot. The front page of the directions for each section, there's a direction that says all figures are drawn to scale unless otherwise stated. Okay? That's an easy assumption to make. However, most of the time, your diagrams will say figure not drawn to scale. Okay? So make sure you look for that because it's important. Because based on what it looks like all those angles are about the same size. Okay? But the figure's not drawn to scale, so you can't make that assumption. You have to use the information that's provided in order to come to a determination. All right? But what we do know is that when we have intersecting lines, the angles that are opposite are congruent. So based on what we know about vertical angles, we can determine that angle Y and angle U are congruent. Ladies, let's stop. We can also conclude that angle X and angle T are congruent, as well as angle W and angle Z. Okay, all of those pairs will be congruent. We're also given this additional piece of information that says the sum of X and Y will be equivalent to the sum of U and W. Now, using that relationship and the fact that we know that Y and U are equivalent, if Y and U have to be the same, X and W also have to be the same. So we can add in that X and W are equivalent because Y and U are the same, and in order for these sums to be the same, X and U have to be the same for X and W. So adding that in, we can also make an additional determination. If X is equal to W and W is equal to Z, by the transitive property, X equals Z and equals W. Okay. X equals Z, which equals W, and X also equals T. So all 4 of those angles have the same measure. Because we know that X equals T, we know that X equals W, and since W equals Z, X also equals Z. So all 4 of those measures are the same. So we just go through and look and see, okay, does X equal Z? Yeah. Does Y equal W? No, Y does not equal W. Y equals U, but doesn't equal W. Does Z equal T? Yeah. So we've got B, 1 and 3. So we use those vertical relationships. Now this problem actually includes a bunch of different relationships. We've got vertical angles, we've got triangle sum theorem, we've got supplementary angles, and we've got isosceles triangles. A lot of information packed in here. We need to solve for X. So there's a couple things that we're going to do to start. A few things to note with diagrams and some of the notation. When you see these tick marks on triangles, it means that those sides are the same length. You don't know what they are, it doesn't matter what they are, just know that they are the same length. When we have the double hash marks, those are sides that are congruent to each other. So these sides equal each other, and those sides equal each other. All right? Now with triangles, when we have side lengths that are the same, the opposite angles will also be the same measure. Okay? So because these 2 side lengths are the same length, these 2 angles will be the same measure. Because these 2 side lengths are the same, these 2 side lengths will be the same measure. All right? I'm using double arches to indicate that they're not the same as the one with the single arches. All right? Now, these aren't vertical angles because these aren't intersecting straight lines. They do bend at an angle, but they do tell us in a relationship that the difference of 180 and z will equal 2 times y, and they tell us what y is. Y is 75, so we can start there to solve for z. So we know that 180 minus the measure of angle z will equal 2 times the measure of y. Y is 75. Go ahead and solve for z. What is the measure of angle z going to be? So the measure of angle z is 30 degrees. Okay? Alright, now that we know this, we can focus on the rest of this triangle. I'm still trying to get to x. Well, in order to get to x, I have to know what this angle is right here. Figure out what that angle is. Alright? Does anyone remember what the sum of all the angles in a triangle is? 90. Not 90, 180. Fun fact, that information is on the SAT reference sheet, like right at the bottom. There's 3 facts, one of which is the sum of all the interior angles of a triangle is 180 degrees. Alright, so we know that all the interior angles have to equal 180. Okay? Well, one of our interior angles is 30. So the sum of the other 2 interior angles have to add up to 150, and since they have to be the same, they have to equal 75. The measure of those 2 angles has to be the same because it's an isosceles triangle, so the measure of those other angles has to be 75 in order for it to sum to 150. Alright? So now that we know this angle is 75, notice that 75 and x form a straight angle. What's the measure of a straight angle? It's also 180. So 180 has to be equivalent to 75 plus the measure of angle x. What does angle x equal? $105. Measure of angle x is 105. So we have a lot of different relationships there. A lot of ratios going on. Nothing too complicated, just requires a little bit of problem solving. It's like pass that down. Alright, we're going to skip the next one because we don't have time. But the same idea. Straight angle, triangle sum theory, straight angle, gets you to x. Alright, let's talk about similar triangles. Similar triangles are nice because if you know about them, it makes your life a whole lot easier. We have a triangle ABC. The measure of angle B is 90 degrees. So let's go ahead and start by drawing. Measure. Got a triangle with a right angle. B is the right angle. A and C will be the other 2 sides, or the other 2 angles, doesn't matter which one's which. Okay, so label it, make sure you pay attention. BC is 16, and AC is 20. What do we call the longest side of a right triangle? The hypotenuse, okay? Alright, we got the hypotenuse. Triangle DEF is similar to ABC, where the vertices DEF correspond to ABC. So D corresponds with A, B with E, and C with F. So we can draw another triangle. Since those angles correspond, since A is first and corresponds with D, this angle is D, E is going to be the right angle, and then F will be this angle up here. Alright, so those correspond. The things with similar triangles is that the ratio of the side lengths will always be the same. Okay, so the ratio of the hypotenuse to the hypotenuse will be the same as the ratio of this leg to this leg and the ratio of this leg to this leg. All right? The other thing that's really, really important about similar triangles is that the corresponding angles will have the same measures. Okay? So whatever the measure of angle C is going to be the measure of angle F. Whatever the measure of angle A is, will be the measure of angle D. And then we see that B and E are the same because they're both right angles. All right? That's the really important part. Each side of triangle DEF is 1/3 the length of the corresponding side of triangle ABC. Okay? So if I wanted to, I could find the measure of the hypotenuse by multiplying by 1/3. And this side is 20/3, this one is 16/3, and this will be some measure divided by 3. But I really don't need to know that. That doesn't really matter. Okay? Because it's just saying, hey, this will be similar. This is the ratio. But what it's asking for is it's asking for the value of sine of F, which is going to be based off of the angle measure. Okay? F is going to be the angle measure. And since we're looking for a ratio, the ratio is always the same. If I'm looking for sine, our sines, cosine, and tangent are ratios of side lengths. Since the ratio of our hypotenuse to the hypotenuse is the same, this side to this side is the same, this side to this side is the same, the measure or the value for sine of F will be equivalent to the measure sine of C, because those are corresponding angles. So once I know that, I don't need this triangle anymore. All I need to know is what sides correspond, or what angle corresponds with F, and it's C. So when I find sine of C, that's giving me sine of F. They're going to be the same. Your trigonometric ratios, our acronym, SOHCAHTOA, helps us remember those ratios. Sine is the ratio of the opposite side over the hypotenuse. Cosine of an angle is the ratio of the adjacent side over the hypotenuse. And tangent of an angle is the opposite over the adjacent. Those ratios will be the same for all similar triangles. No matter how big or small I scale my first triangle, those values will not change. I can multiply these side lengths by 1,000. Sine of C won't change. It'll always be the same. So we just need to find that ratio. So if we're looking at the measure of angle C, and I want the sine, which is the opposite length over the hypotenuse length, what side is opposite angle C? What side is opposite this angle? AB, this one right here, the one that I don't know, right? So I don't know this side, but I do know that I need it for sine. Well, if I have two sides of a right triangle, how can I find the third? Pythagorean theorem, which is what? So let's use a squared plus b squared equals c squared. Our Pythagorean theorem, two sides of a right triangle. I can use that to find the third. Hypotenuse has to be C. Go ahead and solve for B. Okay, so I know my opposite side. I'm going to erase this. I'm running out of room. So the sine of C, which is the opposite over the hypotenuse. My opposite side is 12. What's the measure of the hypotenuse? 20. Simplify that fraction. And since sine of C is equivalent to sine of F, we're done. Sine, cosine, and tangent of similar triangles will always be the same. So we don't need to worry about the 1/3. That's extra information that's there to throw you off. Now, if you want to be a really, really smart cookie, if you divide all of those by 4, what do you get? 4-5 triangle, which is a Pythagorean triple. They like to use Pythagorean triples because if you recognize them, it saves time. So 3, 4, 5 is a common ratio for right triangles. And so if you are aware of Pythagorean triples, you can look and see, okay, well, I have these two pieces of information. I've got 4, or I've got 20, and I've got 16. Both of which can simplify by the same number. I can divide them both by 4 in this case, and it gives me 5 and 4. As long as 5 is the hypotenuse, then we know automatically that this last side has to be a multiple of 3. And so using that information, if you go, oh, okay, well, if I simplify those by the same number, I have 5 and 4. Oh, that's part of a Pythagorean triple. This is going to be side length 3. Well, sine is the ratio of the opposite over the hypotenuse, 3/5. And then you don't even have to do any of that because it is that ratio. I could take 3, 4, 5 and multiply them by anything, say 10, and I get 30, 40, and 50. It's still a 3, 4, 5 triangle, which means that the ratio for sine of that angle will still be 3/5 because 30 over 50 simplifies. So Pythagorean triples are a common shortcut that allow you to demonstrate that you understand it, but also save time without having to do the Pythagorean theorem. It's kind of like when they give factoring problems, they love to include difference of squares, because as long as you know the formula, it's really fast and easy to factor it. You can solve it another way that's much, much longer, but their job is to get you to waste your time if you're not fluent in some of these patterns. Okay? Another way that they get you to waste the time is by including this 1/3. That 1/3 is useless information. They told you they're similar. That's all you need to know about the triangle. It doesn't matter what the side lengths of the other one are, because the ratio will still be the same. Two other types of special triangles. These are actually listed on the reference sheet. Is your 30, 60, 90 triangles. 30, 60, 90. That is not on a scale. As well as your 45, 45, 90 triangles. They have the following side lengths. 1, root 3, and 2. 1, 1, and root 2. Okay? So they follow this pattern. Opposite the 30 degrees is 1, opposite the 60 is root 3, and then our hypotenuse is 2. When we look here, we see we have a right triangle with an angle 60. That means that this one is going to be 30. Same thing over here. Angle 30. This one has to be 60. So there's a couple things that we can learn from this. One is that because this is 30, 60, 90, these are 30, we have an equilateral triangle. 60, 60, 60. Since we have an equilateral triangle, that means that all side lengths are the same. Okay? Second thing that we can look at is knowing that this is a side length 12, and this is a 30, 60, 90 triangle. Opposite the 30, okay, that's the small side. Let's look at our special right triangle here. All right, this is our small side. And this is our hypotenuse. This is our hypotenuse. Okay? How do I get from the small side to the hypotenuse? What can I multiply by? In my special right triangle, 1 times what gives me 2? 2. What times 2 gives me 12? Done. That ratio, they're similar triangles. That ratio is always going to follow through. So because I have a special right triangle, I know that my hypotenuse will be twice the length of the short side. Circles. On the reference sheet says the the internal angle of a circle is 360 degrees. So the measure of the arc in degrees is 360. Here I'm asked to find the length of the minor arc, which is this right here. Whenever you make an angle inside of a circle, so here's our angle, we have a minor arc and a major arc. The minor arc is the smaller one. The major arc is if we went the other way around. That would be our major arc. They want us to find out the length of this minor arc here. We need to find that length. The circumference tells me what part of the circle. All the way around. Circumference is all the way around. So the full measure all the way around the circle is 36 units. Okay? What fraction of the circumference is my minor arc? 1/4. How do you know it's 1/4 there? 4 equal quadrants, right? Also, what's the measure of this angle? 90. If I have 90 degrees out of 360 degrees, that's 1/4 of my circle. So if my circumference is 36, and I want 1/4 of 36, what does that give me? 36 minus 9. Okay? So you can get the measure of the interior angles that's on the reference sheets, right at the bottom, 360 degrees. It also says, right under that, that the length of the arc, or the measure of the arc in radians, is 2 pi. Same idea. We have a central angle, AOB, that has a measure of 5 pi over 4. The area of the sector formed by that angle, so we've got a circle, some angle, okay, not drawn to scale. The measure of that angle is 5 pi over 4. What fraction of the area is this part? Okay, well, we have to know out of the whole. Okay, well, the whole angle in radians is 2 pi. I want to know what is the fraction of my angle out of the whole, the part out of the whole. Well, how do I divide that? 5 pi over 4 divided by 2 pi. Now what? I don't need a common denominator. Multiply by the reciprocal. 5 pi over 4 times the reciprocal. What does that simplify to? Okay, and 5 pi over 8 pi will simplify even more. Pi divided by pi. That's that. It's 1. So it's 5/8 of our circle. Alright. The measure, 2 angles inscribed in the circle. One here, and then one inscribed on the center. Okay? The measure of this angle is 2 times the measure of this one. Okay? X will be equal to 2 times the measure of angle A. Alright? It's one of our circle theorems. In order to find the measure of angle A, split this into an equilateral triangle. Or I'm sorry, not equilateral, isosceles triangle. When we split there, the distance from here to here is the same as the distance from here to here. What do we call that line on a circle? Starts with an R.
Radius.
Right, close. Radius. So we have our radius. Since these are the same, that means that these angles are the same. So what's the measure of this angle right here? 20. What's the measure of this angle here? 20. So what's the measure of angle A? 40. And if x is going to be twice that, what's the measure of angle x? 80. Not so bad. Equilateral triangles, inscribed angles. Inscribed angles are fun. We don't have time to go through this whole thing, but I do want to say if you get lucky, in order to solve this and figure out where the center is, you have to complete the square. When you do, you end up with, I think it was like, I'm totally guessing on that last number. That last number is 100% a guess. Okay, just put that. But the other two are right. When you complete the square, what you end up with is this equation. This is the equation that I like to refer to as center radius. Center radius form. Because what it tells you is the center and the radius of a circle. Here and here gives you the center. But you have to switch the signs. Okay? Because our standard or center radius form of a circle, the formula is as such, where h and k are the center, but since the formula is minus, that means we have to switch the sign. H is 10, so negative 10, k is 8, so it's negative 8. And then if we want the radius, we square root this number, which gives us 15, which would give me my radius. So I have a center located at negative 10, negative 8, with a radius of 15. That's square root 225. So, circle equations, those are fun. It does require the process of completing the square on both of these in order to get that into that and that into that. We'll do more of that later in the year when we have time. Formulas. The formulas for volume are given, cones and spheres, so you'll use those on these. I don't want to spend a ton of time on those. I do want to talk about these real quick. All right. So we have two angles shown. They are acute. Again, not drawn to scale. The sine of angle A is equal to the sine of angle B. We have this identity that sine of an angle is equivalent to cosine of 90 minus the angle. The other identity we have is that if we have sine and cosine, they are going to be complementary. These angles have to add up to 90 degrees. If sine of A is equivalent to cosine of B, these angles have to add up to 90 degrees. And since these angles, cosine of A, actually, since angle A plus angle B have to add up to 90, that means that these two expressions that represent A and B also have to add up to 90. You use that equation to solve, and I don't know what the answer is, but you can solve for K. Alright. Last thing real quick is powers of I. There's a pattern that goes with these whenever you see your imaginary numbers and you need to simplify. Recall that I is the square root of negative 1. Well, I squared would be the square root of negative 1 squared. Well, what happens when I square a square root? Cancels. So I'm left with negative 1. So I squared is equivalent to negative 1. I to the third is the same as having I squared times I. Well, now I know what I squared equals. What does I squared equal? Negative 1. So it's negative 1 times I, which is just negative I. I to the fourth is I squared times I squared. Well, what's I squared equal? Negative 1. What's negative 1 times negative 1? Just 1. Okay? And the pattern continues. So if I had I to the fifth, that's I to the fourth times I. Well, what's I to the fourth? 1. What's 1 times I? It's I. So now I'm back here. I to the fifth is equivalent to I. And if I have I to the sixth, what's I to the fourth? What's I squared? What's 1 times negative 1? And then I'm back here. I to the sixth, I to the seventh, I to the eighth, and so on and so on and so on. So when you're simplifying your imaginary numbers, they follow this pattern.